Now, all right, now we are, okay, so none of that stuff was recorded. That's super great, but this part's recorded. Oops. Um, Welcome, y'all. This is our second Materials Genome Foundation Material Science Demo Day. Our goal for this event is to bring together researchers and developers working in material science and manufacturing to share what they've been doing. We're here to hear experimental work, computational work, theoretical work. The success of this open science initiative requires all of us working together. So we will have a code of conduct. We have not established it yet, and I apologize for that neglect, but we will get to it. So today's policy is a be kind policy. I think everybody can figure out what that means. And let me share with you all the agenda for today. Our agenda is supported by a project called HackMD. It's based on an open source technology called HedgeDoc, which allows for collaborative markdown editing. We use this tool because it connects nicely to GitHub. And when you go there, you'll see the agenda, but you can participate. So if you click on the sign in button in the top right and you scroll down the dialog, you'll find 5 different login options and you can choose one of those. In the agenda, we have a section for July 28th, and underneath of it, we have an attendee list. Let me do this. I'm going to share my screen while I'm talking about this. This makes a lot more sense. Great. Working out the kinks, y'all. Okay. So this is HackMD here. And this is what you'll see. I'm signed in at the moment. If you scroll down a little bit, you'll find we have our agenda for today. So we've started the recording. We'll do some quick intros before we get started. And as I said, our code of conduct today is to be kind. Following that, we'll have demos, lightning talks, and shares. And you can sign up for those in the notes area. So if anybody would like to talk when they're signed in, they can say, do something to the effect, your name, Tony, asynchronous pandas, data frames. That's what I might talk about. So I don't think you guys want to hear about that. So if anybody else wants to hear about things, I suggest you add your name ahead of time. And up at the top here, this is where we keep our attendance. So when you edit in here, you will add your name, you'll add your affiliation, and then if you have one, you'll add your GitHub handle. Now, this part's very important for us. One of the things that we want to do is find more ways for people to participate in the software side of material science. And contribution is very important in the long run. So this will help us make sure that we stay connected with you all on coding platforms, and that we're also helping onboard people into a more open science network. So with that, I think it would be really fun to do some very short intros. So let's try and keep these brief. And I'm going to call out names. Or actually, let's do it this way. At the bottom of Jitsi, there's a hand. If you would like to introduce yourself, raise your hand, and I will call on you. So I'm going to start. My name's Tony Fast. I am the strategic planning lead for the Materials Genome Foundation. I'm also a distinguished contributor for Project Jupiter. My background's in material science, and I'm really interested in making more people, more material scientists on GitHub. I do not see any other hands up. Cool. Adam, great. Thank you.
I'm a 4th year PhD student in Dr. Zikuli's group, who is here in the meeting. I mostly develop software related to machine learning and data processing in material science. It's my second meeting, and I love the previous one, so that's why I came back. Oh,
That's
and
great to hear.
I'm currently at Lawrence Livermore for the summer.
Excellent. The hope is to keep folks coming on back. So is there anybody else who'd like to do an intro? Yeah, Richard.
Yeah, hello. My name is Richard Otis. I am the managing director for the Materials Genome Foundation, also associated with NASA Jet Propulsion Laboratory. I'm really passionate about research software engineering and helping to better connect material scientists to great software tools and help them become builders of great software tools. Thanks.
Thank you for being here. All right. Leave a little bit more time if anybody wants to say anything about themselves. All right, Ridwan, please.
Hey, I just got the email last night from Zikwe, so I thought, hey, what the heck? Let's join. Uh, I'm a physics and material science professor in Missouri State, and so I thought this is really wonderful, opportunity and be able to chat and, of course, drink coffee. That's
Yeah. Maybe we call it coffee hour.
That's right.
There you go.
We should take a picture together, like doing this.
It's all streaming right now, so we can just take a still of that later. But yeah.
Anyway, my interest is mostly in atomistic simulation, particularly in, there's the word I guess I would call, and I'm borrowing this from somebody else, actually, from Kristen Person's group, which is to democratize atomic simulations, which by means of essentially being able to have the ability to have more community joining in making atomic interatomic potentials using either machine learning in general or a neural network. So that's basically my goal, and be able to see this can be disseminated in large scale, so people can actually model more and more complex materials. Okay, that's all.
We're all on the same mission. It's great to hear. That democratization doesn't happen without a degree of openness to it. So yeah, thank you. That's exciting, and it's good to hear about that kind of growth. Any more intros? Brandon.
Hey everybody, I'm sure a lot of you know me, but I'm Brandon Bachland. I'm a board member of the Materials Genome Foundation, also a postdoc at Lawrence Livermore National Laboratory. I work mostly on PyCalFat and SPay, but also do a lot in the DFT atomistic space. I'm also really interested in getting tools and new methods out there for people to use.
Thanks for being here. All right. Any more? All right, Jorge. If you keep quiet long enough, everybody talks. It's a skill.
Hello, I'm Jorge. My last name is kind of long, but Paso de Palma. You don't have to say the whole thing. But I am currently a postdoctoral fellow at the University of South Carolina, and I also work on PyCalFat and SPay, like a lot of the people in this, well, Richard and Brandon. And but although I don't directly do any more DFT calculations, I do work closely with people in the university who do DFT calculations. And thank you for inviting.
Very cool. One day I'm going to see it. If I run this meeting long enough, one day I'm going to see a demo of PyCalFat or SPay. I'm still learning about these tools, but I feel like I'm definitely not part of the in-group yet, but I'll get there. I'll get there. All right, there's a few more folks who haven't done introductions. If you'd like to raise your hand, I'm going to keep silent for another 10 seconds. And then after our intros, we'll move into the demo portion of the event. Sikwe.
All right, I'm trying to get my system working. Looks like it works well now. My name is Ziguelio. I'm Professor Penn State. And I see some familiar faces here, some new faces too. Actually, quite a few new faces here. That's great. Well, I have been here now for 25 years. I always talk about retirement, but I may still stay here a little bit longer. I want to thank Tony for joining Materials Genome Foundation and for the wonderful thing you have done so far. Looking forward to continued interactions. Thank you.
Cool. Thank you. Man, this is a great room. It's a pleasure to have you all here. Any last introductions, and then we get into the technical part of this. All right. Well, so this is what everybody's here for. This is a very freeform portion of the event. And if you don't feel inspired to share just yet, and you find yourself along the way feeling inspired to share, let us know in the chat or yell out your name. But if anybody has any demos they'd like to share, any recent research, and if anybody would like to talk about any software problems that they're having, now's a great opportunity for that. So effectively, that's what we've dedicated this whole time, the rest of this time to. So if anybody would like to share anything, please, let me
Tony,
know.
I have a question for people that share about how long do you want each share to be?
Yeah, let's try and shoot for 5 to 10 minutes or so. And kind of keep it around 5 minutes, and then leave some time for a discussion. So at the software conferences, I don't know if y'all do this at the material science conferences, but like the highlight of everything are lightning talks. Has anybody seen a lightning talk before? If you have, throw your hand up there. But yeah, lightning talks are fun, right? They're exciting. Yeah. So the idea is that for folks who didn't get a talk in the conference, they put a sign-up sheet, and you go on stage and you have 5 minutes to present. They're really exciting, and it's actually I remember doing these when I first came from the sciences, and I found that I was very verbose, and it definitely taught me to tighten up my stories a little bit. So lightning talks, 5 to 10 minutes, and the content that is up to you. Does anybody have anything they'd like to demo? One thing I'm gonna call. This is not fair of me to do, but Adam, if you would like to share your demo again, since we are recording, that would be pretty cool. But if anybody else has anything, please let us know.
Give me a minute to prepare.
Great. Take your time. Hey, Richard, what do you think if I did like a short demo of what our strategic plan is looking like right now and our goals, so that maybe people can understand what we're thinking?
I want to wait a little bit longer, maybe next week, because we're meeting about it later today.
Good point. We haven't all synced yet.
Yes. Let's do that, and then I think maybe we could do it next week.
Yeah, that makes a lot of sense. That sounds great to me. Cool. All right. Okay. Does anybody have any PyCalFat or SBay demos that they, or any work that they could, overviews or anything they might be interested in sharing with us? Or any software or any non-software. Experimental pictures are pretty. Okay.
Yeah. So one thing I'll say, Tony, I have a couple of PyCalFed related things that I could share. We are right now on our push over this next. Let's say we're targeting 2024 to release PyCalFed 1.0, and we have a number of features that we're trying to complete and get merged in and be ready to go. We have one of them I think is pretty exciting, which we call the Workspace API, and I could show a little bit about that today. That's a possibility.
Yeah.
Or if somebody else wanted to talk about something else about PyCalFed as well, that'd also be fine. I mean, this doesn't have to be about PyCalFed, but
pull requests can totally be a valid topic. Like one pull request can definitely fill up some time. So if there's outstanding pull requests that are works in progress, that stuff's good to hear. I mean, actually, the hard part of open science is the work part. You forget about all that stuff when you just are using the software.
Yeah, well, I can start with that and hopefully still be a good be something interesting to this group. Let me see if I can get my share going here.
No problem. Take your time.
Okay, is it coming through here? My screen?
Indeed, crispy.
Yeah. Okay. So this is I'll try to keep this short, and people that are interested can go and read more about this. So this is a PyCalFed pull request. I'm definitely very excited about. As you can see now, we're actually closing in on almost a year of working on this. This, which is called the Workspace API, and you can look this up. This is on GitHub, public pull request 432, and what it does, in short, is it adds this new object to PyCalFed called the workspace, and it does a whole bunch of other things. But I think probably the best way to explain what it does is just to show you. And so I have a couple of pieces here that I can share. And actually, the best thing to do is probably just to open a brand new notebook, and I should be loaded into. Make sure I have the correct PyCalFed checked out here. And I do. And so I'll just kind of show you an idea about how this works. So many of you will know that, typically for PyCalFed, when we are doing calculations, like equilibrium calculations or plotting and things like that, it can be kind of a hassle, right? So for example, if we look at plotting phase diagrams, you create a database object. We have these bin plot objects that can help. And then, for plotting out phase diagram or for plotting out energy, right? So energy versus composition, this is a very common plot to do. There's a lot of boilerplate code to do this. And we've gotten a lot of feedback over time. And it's similar even for something as simple as calculating a heat capacity. There's a good bit of additional information that has to be specified, and getting these plots correct. We wanted to help. Let me
interrupt you real quickly. Can you do me a favor and close out the file browser, and then click on view presentation mode? Is it down there?
Oh, there it is.
Yeah, nice. That just bumps up text a little bit.
Yeah, I can also do a little bit like this. Yeah,
and then single document mode down the bottom left.
Bottom left.
Hit that simple thing. Oops, just to the left there. There you go. Nice.
Okay, is that better?
Yeah, great. Looks great.
Okay, great. Thanks. Yeah, Tony and I didn't coordinate any of this in advance, so we're figuring out in real time. So the idea of the workspace is that you can actually define the object step by step. So, for example, you could write like this, and then now you set the database. right? And then now if I go and look, I actually have a database object there that's specified. And the other thing I can do is I can go and look at the phases, and I can see that already my phases have been selected. I can look at the components, and I can see the components have already been loaded in. And now I can start doing calculations, right? So for example, I need to set my conditions as well, right? So what I can do for my conditions is I could write it as a whole dictionary, or what I could do is I can write, 500, to set the temperature, right? And then if I go and look at the conditions, what's the best way to look at the conditions? Well, let's hold on for a minute. But you can set the pressure and so on. Anyway, I don't want to take up the whole time with that part of it, because this isn't the most interesting part. But you can then go and set the zinc content. Yes, I think that should still be good. And so then finally what I can do is then I can go and call, I want to get the Gibbs energy for this, right? And so it gives me the Gibbs energy. So you notice that you can already do this, right? You can use the equilibrium function to do this, but now you can modify things and mutate the workspace object and then call out the function. And this only scratches the surface of what the workspace object can do. So now what I'm going to do is I'm going to switch back over to here and show you a little bit more about what can be done. So this is a more complex example, but I just wanted to show you the initial idea first. So here, what I'm doing is I'm creating the entire workspace object in advance. So this is, you can do it step by step, or you can just specify everything initially and then mutate it later. So what I'm doing here is I'm doing a temperature step calculation at constant zinc content. And then what I'm going to do is I'm going to use the plot function. And so the plot function here is like, it like takes the get function, but then it's integrated with matplotlib to be able to plot things together. And it also has support for specifying units. So for example, let me just show you an example here. So like, what I can do is I can plot the temperature in degrees Celsius. And then let's say I just want to plot the phase fraction of all the phases, right? Common thing people wanted to do all the time. It used to take a lot of boilerplate code to do this. And now you can see it's actually pretty easy to plot that. Oh, and actually I want that in Rankine, right? And it'll do the unit conversion for you. Or if you just want it in Kelvin, you could specify. So this is built on top of Pint, the library Pint, to make it easy to be able to do these kinds of things. And so we're really excited about this, and I'm already using a lot of time. The other thing that we've added is support for dot derivatives. So if you're familiar with thermocalc, the ability to compute constrained thermodynamic derivatives. So like for the heat capacity, it's defined as the molar enthalpy, the derivative of the molar enthalpy with respect to temperature. So now you can use this as property function to be able to write the property out like this. You can pass in any string and then call as property and then define the units that you want, right? So like, if I comment that out for a second, you see the default units are joules per Kelvin per mole, but I can also use this unit specifier to say, well, actually, I want this in millijoules per micrograms per degrees Celsius. So we also support the gram to mole conversion here as well, right? So then if I rerun it, you can see it does the unit conversion for you automatically. So we're still working on this. There's a lot of other pieces of this to show here. I don't have time to go through it all, including new driving force calculation features and things like that. But we're really excited about this, and we're working hard to make it easy to do, kind of these sort of simple everyday calculations in PyCalFat and help you to better explore your data. So anyway, I could spend a whole hour on this, but I just wanted to give a little bit of a hint about what's coming, ideally in 2024.
Who's excited about this? It seems really cool. Yeah, Jorge.
Nothing. I'm just excited. That's what I meant.
Yeah. Adam.
It seems like it's going to be much easier for new users to use PyCalphat now. Just get started and see exactly what's happening and why and how to tune it to your needs.
That's the idea, and also the ability I didn't show, but also the ability to build custom properties also, so that what we kept hearing over and over from people was just plotting properties in PyCalphat is too hard. And as an occasional user of PyCalphat myself, it was annoying. I found myself constantly having to look things up in the documentation. How do I do this again? And if I'm doing it, then new users are definitely having trouble. So that was part of the motivation for developing this feature.
Really cool demo. The unit stuff was cool. Curious. I've got lots of questions for you. Let me see if other people have questions. Yeah, Ridwan, please.
Oh yeah. I frankly I'm very new at this, so forgive my little bit of ignorance here. But I thought I heard somebody was talking about machine learning, and I wonder, was there any efforts in integrating that into the code, or is there any, for example, just hypothetical, let's say if you're trying to discern some single phase regions of, I don't know, high entropy oxide or something like that, is there a sort of efforts toward that directions? I thought I heard somebody, maybe one of Professor Liu student or postdoc, that was talking about going to that directions. I'd be very curious about that.
Yeah, I think this would be a really good segue into Adam's share for today, because I think he has some really great ML work in exactly what you're asking about.
Thank you.
I was going to show some non-ML work, more only data analysis.
Oh, okay.
But,
show that.
I guess before I do that, I can kind of segue that Brandon created this really nice piece of software, SPay, that can combine data from multiple sources and optimize databases in this way. And one of the inputs to that software can be some sort of machine learning prediction, for example, for formation energy. And one of the tools I'm working on is called PySipFan, that can provide you this kind of input. And then get processed into a TDB with SPay. So there is a path for it. We are still polishing it, but it's going to be very nice in the future if we succeed at making it smooth. So today I'm going to show.
Let me finish up with some questions with Richard before we move on. Is that all right? So the visualizations there, they're all Matplotlib. Have you explored any of the other visualization backends for that, like give like more interactivity and stuff like that? Like say Bokeh, do features like that like add to the software experience?
So I have used them before. I have used some other visualization libraries, including Bokeh, even to plot things with PyCalFad. But so the way that it's set up currently is we've abstracted the plot rendering stuff from the property stuff. So you can implement a custom renderer, right? So there's a Matplotlib renderer that basically takes in the arrays that are created by the calculator. So the renderer doesn't have to know anything about the calculator, basically.
Great.
So you could add in for Bokeh. We went with Matplotlib to start because it's already a PyCalFad dependency. But other renderers could easily be added. Right. I mean, definitely, Plotly or some of these other tools out there, they could be good fits for this as well. Yeah. Would welcome input on that. Actually, I feel I'm at my weakest when I'm trying to optimize a lot of the visualization stuff, and I prefer the numerical stuff. So,
well, that kind of gets to my next question, which is the interesting thing that I see in what you all are doing is convergence of the science and the software, right? So like in this, you're designing science, and then you're also designing an API. And one of those things you're trained in, and one of those things we're not trained in, right? So, like how have you found like managing the balance between the science and the software? Yeah, how's that complexity? Like, do you think that complexity contributes to maybe some of these PRs being a little bit longer, or are there?
It absolutely does. Brandon, in particular, can tell you about how I have this this tendency. I won't call it an annoying tendency because he hasn't told me it's annoying, but I could imagine it's annoying. Which is that my pull requests tend to get really big. They grow into these thousands of lines monstrosities because I don't naturally think to, or it doesn't feel correct to me that I would break things up into smaller features and merge them in, because it doesn't feel like it tells the story yet. And I often will let my development branches grow until they're I feel like they're ready.
Right.
But then they become kind of hard to review, right?
Right.
We've been working on this for more than a year, but arguably maybe some of this could have gone in sooner. And part of that is that I wasn't able to figure out how to break them up into smaller pieces.
Sure.
Right. It all needs to go together. Yeah.
It's not apparent when you're writing it, right? Like, so it's it's a medium, and eventually it tells you that you can and cannot do this, right? So you never really know. One of the things that I've been experimenting with personally has been Git tree. I don't know if you're familiar with Git tree, but it allows you to have multiple pull requests merge into a single change, right? So basically you can be working on a visualization pull request, a model pull request, and have those things sort of synthesized and separate out the scope in that way. So it's a really advanced Git feature, but when you do run into these like really interdisciplinary software problems, I'm kind of wondering if it's not an effective approach. Neat. Well, Adam, do you want to share some data stuff?
Sure.
Great.
I'm wondering if, for the sake of time, should I go over the PyQ alloy I showed last week, or maybe show something new? Because I got one feature for PyCipFun that I was working on for a while now, and now it's stable and works nicely. So maybe I'm going to show that, and that's going to go into Ridwan's question. So to give you a brief introduction first, when you do this kind of featurization and prediction of properties for atomic structures, usually you put in some compound, or maybe an SQS structure if you want to approximate a random solution. And then that featurizer is going to go over all the atomic sites, whether if it's represented as in our case with PyCipFun, it's just a collection of unique chemical sites that you find in a structure, Wigner seed cells, and then describe that Wigner seed cell, and then do statistics over all of them. Or it can be a graph where you move over all the nodes. But in general, what's going to happen is you're going to have some predefined structure that you put in, and then you get some output that you get out of it. But when you move to complex alloys like high entropy alloys, you're going to start running into problems where you have some SQS, let's say, but that SQS is either going to be some approximation of an SQS, and that one is or the true special quasi-random structure that is the best representation of that random solution, or you're gonna try to combine multiple ones. But in general, you're never gonna end up with something that is exactly the random solution, and it's gonna be probably expensive to compute. So what we were thinking about is whether we can try to look at how the structure is gonna converge in feature space when we expand the supercell by populating it randomly as we expand. And let me share the screen now. Perfect. Can you see now? Okay, so
Yes.
I just added that feature to one of the branches in PyCipFun. But what this function is doing is, well, you can read the documentation. It's pretty long, but it explains all the parameters you can set, and it's gonna take that structure that you give it. It can be any sort of structure. It can be just a BC lattice, or it can be some more complex one. And then it expands the structure iteratively in all the dimensions. And at each expansion, it's gonna calculate what is the composition distance from the target composition that you're trying to featureize. It's gonna look at all the features and try to figure out if all of them converge onto some convergence criterion, and also if all of the atoms occurred in the structure at least a certain number of times. And then it featureizes it using the featureizer I mentioned before that goes over all the unique sites in the cell, and it then gives you a result for the expanded cell. And we do deploy that onto our high entropy alloy database. It was actually going on as I started speaking, but I interrupted it so that I can show you an example where we are going to use it to featureize BC single cell solution of tantalum, tungsten, rhenium, ruthenium. And I ran it with plot parameters and print progress through so that you can see how it expands. It's fairly fast. You could see that in 7 seconds we get 330 atoms featureized, and after a couple iterations, all of the features that PyCipFun calculates, there are 250 of them, converged onto within in this case the default 1% of the maximum value of the feature found in OKMD, and we got the feature vector, which now we can use to run, let's say, PyCipFun, and get the formation energy of that random solution structure, or we can use other tools which are gonna be in the next workshop we do, to, for example, look at how these random solutions are distant from some ordered structures, and also one other feature that will be coming is addition of SQS-like structure generator that tries to get the same result based on lower number of sites. And that's my quick lightning talk for something I got to work last week.
Hey, congratulations! Was it a long haul to get there?
If I was single tracked on this, probably not. But yeah. I work on a lot of things, and you know how it is. There's a lot of things I have to manage at the same time, and it was something that people were asking me quite a lot, and especially when I went for a CalFed conference in Boston, I got a few people to ask for it. So I sat down last weekend and I got it to work finally.
Very nice. PyCharm looks great.
It does.
PyCharm looks awesome. Yeah. There's something to be said for paid products.
Well, I have the student account.
Fancy. Yeah, that helps.
But the new UI that they released in this year, it's I was very skeptical at the beginning because I like this kind of bare bone or feature rich, but graphics not so rich UIs, where everything is there instead of icons like in VS Code.
Right. Yeah, Ridwan.
Excellent. Forgive me. I can't find where the icon I can do times up in this thing. Usually, I can find it in Zoom.
So thumbs up is if where the hand is. There's a little arrow there. If you hover over the arrow, thumbs up pops up, and then you can just do Alt T And
All right. Okay.
yeah.
I just did that. All right. Thank you. The question I have is basically I think one of the I would think like a futuristic, maybe it's already done by companies, is really obviously to use this again. This is within the view of democratizing, is using it almost regularly, let's say in your electron microscope, right? In other words, you can run like a EDS map, and then immediately you would be able to get the whole face, essentially a makeup, or something like a classifier type of analysis, basically maybe using Bayesian. So because that would be much quicker obviously than doing the whole calculations, which you can imagine like almost like a face recognition type of thing. Basically, is there a direction on that? And maybe this is, again, maybe this is my full ignorance, that people can just do EDS and then they be able to get like a within some certainty about what phases that are in there, using basically this more reduced machine learning, less intensive calculations, and then can be done as quickly as basically doing EDS.
I'm not an expert in EDS, so take it with a grain of salt. But when we have some experimental colleagues, and last year they found out that there was a structure in neodymium bismuth system where they couldn't recognize it based on previously known structures. And what we did is we ran we took a large data set of atomic structures we have. It's called MPDD. And then we tried to find all the structures in MPDD that would match that stoichiometry that they were observing in ED, I think it was an EDS map. And then we we ran we replaced all the species with the target composition. Then there were hundreds of thousands of them. We ran predictions for what's the formation energy for each one of them. And then we selected a set of representative samples from the low energy predicted structures. Then ran DFT on that, and one of them was a match to the XRD pattern that we were getting afterwards.
Okay,
And
excellent.
it was some exotic one, anti-lanthanum structure, I think. I'm a data person. I was super excited that the tool worked for them. But I can give you a paper, and I can also put a link to the PyCyphin itself.
All right, thank you.
That's an incredible story. Thanks for sharing those links in the chat. That was a great demo. Any more questions for Adam? Yeah, nice stuff. All right. Is anybody inspired to share or talk about any things? Any comments or questions? Any general things?
And I'll echo what Tony said earlier too. If you've run into a problem with something, particularly code related ones, particularly probably this audience could help with. This is also an opportunity if you would like your share to ask a question to this group. That is also allowed and welcome.
Yeah, more to that point. I'll drop a link in just a second. Actually, trying to record these links that Adam's sharing here. But we're hopefully this is the last time we do this on Jitsi. Where we have not done much to it yet, except for acknowledge its existence. But I believe next week we'll be meeting on our Discord. And we want to use the Discord as a place to, kind of bring these ambiguous software and science problems to the fore. So we'll be able to use this community and our network to solve problems together. If it's late night and you're banging your head against something and you really just need somebody to talk to, maybe this will be the place. But this software work takes a community too. Like Adam seems really fortunate to have a nice IDE set up, and like I really think that there's an element of self-care in having a good IDE, but too many people haven't really taken the time to explore like their IDE, and some of that stuff actually affects progress, in my opinion. Happy developers, happy software kind of thing, right? So encourage yourself and other people to like take time, find the right extensions, find the right settings, and like that will improve the comfort and quality of the work that comes out. At least I believe personally.
I definitely agree with you on that, Tony.
I like VS Code though. It scares me how much attention that project has, like as far as like all the developers. But yeah, that project's been suiting me very well. But like when you started a few years ago, it wasn't great. Are you Vim or Emacs?
Me?
Yeah.
I don't use either. Well, I've probably used Vim more than Emacs, but I actually prefer the Nano text editor.
Oh, nice.
When I have to edit on the command line, which is not super often, but yeah.
The first 2 years I used Git, and I'd like make a commit and forget to close out my string. And then I'd get into Vim, and I had no idea what hellish nightmare I'd fallen into. I just closed the terminal window, like an hour and a half of work. I just closed the terminal window and then like have to open it up because I had no idea what was happening. It took me forever to figure out like the clumsiness of IDs a while ago. Very neat. Well, hey, it was a super great discussion, y'all. Thank you to Adam and Richard for presenting on the fly and everybody's participation. We hope to do this weekly. Our goal with the Materials Genome Foundation is to build an open science community focused on material science and manufacturing. So your participation here contributes to that mission. Thank you for your time. Yeah, we're going to do this again next week. And if you enjoyed yourself, we hope to see you again. And hopefully, if you can't join next week, we'll be here in a month. We want to keep doing these things. And if you think it's a good environment, please bring a friend along or invite a friend, tell your students, tell your colleagues. But we really want to hear more about what is going on with the people writing software, working with data, working with models, trying to put all these things together. We want to help. We want to work with that community. So thank you all.
Thank you.
Thank you. Yeah, I'm going to stop the live stream now. Y'all can feel